Hi, David Bridges, MEEN 3335, Intro to UAS, Unit 3, Lecture 3, the Proceras Kestrel Autopilot. And the purpose of this particular lecture is to gain a basic knowledge of the components of the autopilot for an unmanned aircraft system. So we want to see what goes into an autopilot. We've already talked about sensors and all that kind of stuff, but we're going to see what everything goes into an autopilot. We're going to look at the functions of each of the components and how they interact. And then we're going to look at this idea of waypoints and see how they can be used to, you could basically write like a program to conduct a mission. Okay, and so we'll look at that. So, as I said in the previous lecture, this is a repeat of that slide. And again, the reason I'm using this particular document is because it has everything in it. It has the hardware development, it has the firmware development, software development, it's all in there. And it's free. And so all the figures, just right up front, all the figures from this lecture are coming from that thesis. Okay, so this was the aircraft that they were going to use, and it's a Zagi THL flying wing that they retrofitted with an electric motor. Okay. Now, remember they had to develop what are called the control laws. They had to figure out the system response. And so what you see here is the response to a particular input. So this is called an aileron doublet, where you basically instantaneously, deploy the ailerons. Those are the control surfaces on the rears of the wings, which will cause the airplane to roll. So you deploy them one way, and then after a certain length of time, you return them to zero. And that's referred to as a doublet. And so what happens to the, phi is the bank angle, and basically it banks and then holds at a like 0.75 degrees roughly. Now because it's banked, the heading is going to continuously change. That's psi, so that's the second curve. And then the bottom is the, I'm not sure what P is, but okay, so you see the step change in the aileron. P is one of the rates, and I forget right at the moment. But this is the response of the airplane. This is one of those pieces of information that you need to go into the control system and develop it. The PID controller that we talked about earlier. Remember, I talked about moving the mass up a unit and seeing how it responds. Well, this is basically the aircraft response to this particular control input. So you see how big it is. Okay. All right. So they determined that, just in flight testing, that it had both longitudinal and lateral instabilities. In other words, if it started pitching up and down, it would get bigger and so smaller. So then basically the autopilot also becomes a stability augmentation system, because you want stable autonomous flight. So you had to actually develop pieces of the control system that would simply make sure the airplane was stable. Okay. So this particular section of the thesis discusses the proportional integral derivative control structure that they developed to stabilize and control the aircraft. To fly it autonomously, you want it to be able to go through waypoints. The requirement that in between the waypoints, the heading, altitude, and airspeed should be maintained. And then also for manual control, you want to basically be able to switch from autonomous to manual in case you need to take over manual control for some reason. So it had to accept pitch and roll angle commands. Now, because it's a flying wing and it doesn't have all the control surfaces. Basically, it only has ailerons and actually, I think it may just be ailerons, because if the ailerons move together, they basically act as the elevator. And if they move separately, they act as the aileron. So you can get, when they move together as the elevator, you get pitch, and when they move independently as ailerons, you get roll. And that's really all you can control on this thing. I don't think it has specific, there was no active rudder, so there's no specific yaw command. Okay, so, all right, so we're going to design the controller. So you could use a nested PID loops, okay, that control the aileron, elevator, and again, the ailerons when they move independently, elevators when they move together, and throttle. You want to change the speed. Controlled via the inner PID loops to stabilize the roll, pitch, and throttle. Then the altitude and heading are controlled with outer loops, which produce commanded values for the inner loops. Okay, so if you want to go altitude and heading, you've got to figure out what you're going to tell the aileron, the elevator, so forth. So as is typical in aircraft design, you divide the controller into two separate controllers, the lateral controller and the longitudinal controller. That's just natural to aircraft. The pitch controls separate out naturally from the roll and yaw controls. All right, so here's the longitudinal control, low-level control. Basically, this is the altitude control loop. So you have the desired altitude, measured altitude is a feedback control loop, and then Kp plus Ki over S plus Kd times S, basically. That's proportional, integral, differential. So proportional is just a constant. If you integrate the signal in the S domain, 1 over S is integration. If you multiply by S, that's differentiation. So Kp plus Ki over S plus Kd times S. Kd, Ki, and Kp, Ki, and Kd are just constants. So you have a constant plus a constant over S plus a constant times S. That's proportional, integral, differential, or derivative. Then there's what's called a saturation block, which is what happens if you try to over control. And you basically, you control the aileron up to a certain point and you just can't go any further. Okay, so there's referred to as a saturation block. And then out comes the desired pitch. Once you've done all that, you get the particular pitch angle that you want that's going to take you to the desired altitude. Okay. And so here is the pitch input and response. The dashed line is the input, so that's the desired pitch angle. So basically they want to go 5 seconds, 0, and then they want to go up to 16 degrees for 7 seconds or whatever, excuse me, 13 seconds or whatever, come down to minus 17 for a number of seconds and go back up to 0. And that's also sometimes referred to as a doublet. And then you see how it responded. And so it's not bad, it's pretty good. Not exact, but so you see the input and the response, but it comes up to the desired value pretty quickly and levels off. There's not a lot of oscillations. So this is a good controller. Okay, they did a good job on this. Okay, well that was the easy part. So now we're going to talk about the whole system. So this is a system diagram. We're going to see a lot of these kinds of diagrams. So let's look in this block in the upper left corner first. This is what's on the airplane. So notice you've got sensors. It says pressure, gyros, accelerometers. You've got GPS receiver. Okay, those go into this computer which has the autopilot software. Okay. There's a modem there. That's basically a digital radio thing, and we'll talk about modems a little bit later in the course. We'll talk about communications. But that modem basically is how you talk to this thing. All right, so these are the avionics on the airplane. Now, that's the avionics block. You see the block on the right. It says flight platform. And there's a block there, the airplane hardware. That is that's the aileron. That's the throttle control. That's the elevator. All right. Now you see above it bypass switch. Well, if you go down to the block below, you'll see something called development hardware. There's the human pilot, okay, and this transmitter. All right. So what happens is, so this bypass switch, and we'll talk more about it later, but the bypass switch is taking inputs from the autopilot and from the manual pilot on the ground. And there's a way, and we'll talk about this again a little bit later, but there's a way it decides which one to pass on to the airplane hardware. If you're supposed to be flying on autopilot and everything's okay, then the bypass switch will say, all right, inputs from the autopilot will go to the hardware, the elevator, rudder, and so forth. If there's a problem, if I get a particular signal that says there's a problem and I need to give control to the guy on the ground with the joysticks, then the bypass switch will say, all right, the input from the ground controller will go to the hardware. All right, so that's how it goes between autopilot and manual. We'll talk about specifically the input that allows it to do that. Now, and then in the middle, there's, everything in this upper big block is the airborne hardware, and everything in the bottom big block is the ground hardware. So the middle smaller block in the big upper block is the payload. And this particular system just has a video camera, and then it has an analog video transmitter. All right, so it takes the video camera, sends its output to the ground by 2.4 gigahertz analog video transmitter. Then there's a corresponding receiver on the ground and a frame grabber or a video monitor. Okay, so you basically have a screen there where you can look at what's coming off the airplane. All right. Now, if we go all the way to the bottom, again on the left, the ground hardware, you see the autopilot ground station hardware. This is the laptop, which you're talking to the airplane with, and you're controlling the airplane through the laptop, and it's connected to this 900 megahertz digital modem. Okay, and again, that's basically just a digital radio, but we'll talk about modems a little more later. So that's talking to the autopilot. So you've got the laptop that's talking to the autopilot through the 900 megahertz link. The autopilot is taking in the information from the sensors and sending control information to the bypass switch, which is then sending it to the airplane hardware if it's okay. If there's a problem, then this bypass switch is taking the input from the guy on the ground with the manual control, sending it to the hardware. In the meantime, the payload is capturing video images for the video camera, transmitting them to the ground through a 2.4 gigahertz video transmitter link, being received on the ground and then viewed through a computer monitor, frame grabber, whatever. This is standard operating procedure. This is the way our system works. But there it is, all laid out for your viewing pleasure. Now, let's start looking at some of those pieces. All right. So first of all, let's look at the autopilot board. This is a block diagram for the main board. And again, you see there's a sensor system. So you have the IMU sensors, rate, gyros, and accelerometers. You have the pressure sensors, voltage and current, auxiliary ports. You have the A to D converters. They take those analog signals that come out of the accelerometers and everything, convert them to digital. Okay, so that's the sensor system. And that information gets passed to this core. All right. Then there's a payload interface where you're talking, this is kind of a separate thing where you're talking to the payload, supporting electronics. This is just the power going into the autopilot and power going to the motor and all that kind of stuff. All right. So this core module, 6 serial ports, 50 general purpose I/O ports. It's basically a microprocessor. Okay, on board. The CPO is responsible for processing sensor data, handling the input-output to the GPS, the modem, and the bypass circuit, running the low-level control algorithms, and handling communications with the ground station. Okay, so that's the CPU here on the autopilot board. All right, so now let's talk about the sensors that are built into this thing. So X is the inertial position of the UAV along X1, which is the north direction. So basically north and east are the coordinates parallel to the ground. And X and Y are measured by GPS. Okay. Altitude is measured using a chip-mounted absolute pressure sensor, okay, in the standard atmosphere. The pressure airspeed is the indicated airspeed. That's measured using differential pressure, again with a differential pressure sensor, chip-based, basically. Beta is the side slip angle. It's not measured. Alpha is the angle of attack. It's not measured. The roll, pitch, and yaw angles are not directly sensed, but they're obtained through the rate gyros, which do give you the body fixed roll, pitch, and yaw rates. Okay, so you have 3 different rate gyros. And that gives you the roll rate, which is the roll about the x-axis out the nose. The pitch rate is the nose up or down rate, and it's about the axis, the y-axis, which goes out the right wing. And the yaw rate is basically the we all about the vertical axis, which is perpendicular to X and Y, and goes, it's actually usually measured positive down, so you have a right-handed coordinate system. So that's what's measured. Okay. And they also have accelerometers on board. Well, it's not in that list, but they are measured. So we have the rate gyros, which directly measure P, Q, and R. And you see how big these things are. That's a penny. And so you see basically three of these things in the corner. So the three axes are, they're perpendicular to each other. So they're measuring three axes relative to the airplane. Okay. So the rate gyros and accelerometers are mounted orthogonally, such that rotational rates and accelerations about the body axes can be sensed. Okay. And then you take that output, you put it through a Kalman filter, and you get an estimate of roll, pitch, and yaw. Okay, so this is how that's done. A block dot. So now we're talking about the software. Now we're talking about the control algorithms, all that kind of stuff. How it takes all these different measurements and then figures out what it's doing. All right. Well, it uses a Kalman filter, but this time the prediction and correction are a little bit different because now we're talking about attitude at the moment. We're talking about roll and pitch angles. So GPS doesn't come into it. GPS basically only gives you the location of the center of mass of the airplane, more or less. So GPS is not going to tell you if you're rolled. Okay, it's just going to tell you where you are. Okay. So there's a predictor corrector step here that's used, and the predictor step is basically using gravity. Okay, so gravity always points vertically downward, but if you're banked or rolled, that vertical downward is not going to coincide with one of the three axes of the airplane. If the airplane is wings level, nose level, then the z-axis is vertically down, and the gravity vector will be in the z direction. Okay, so you'll read 9.81 meters per second squared in the z direction if you're flying that way. But if you're banked or pitched or whatever, then the gravity vector is not pointing straight down from the bottom of the aircraft, it's pointing straight down toward the ground. So the accelerometers will pick up that components of gravity in the three directions which are attached to the airplane. Okay, the coordinate system, because of where these things are mounted fixed to the airplane, the coordinate system is attached to the airplane. Okay, and so when you're pitched and rolled, then the gravity vector has components, shows up as components in the three coordinate directions. So you can use that information, as you see in the formulas at the top, to get a first estimate of the orientation of the airplane, the pitch and the roll and the heading. Okay. Then the next step is you use the rate gyros. Okay. So you calculate pitch and roll and pitch angles. Okay, so you integrate once and get those, and that becomes the corrector step. Okay, and so then you put these two together. So you basically, so each one individually is running a Kalman filter. So you're using the previous state to update the current state, and so forth, for both of them. But then you put them together to get the updated estimate of roll and pitch. Okay. This process minimizes the integration error caused by rate gyro drift. So you've got basically two Kalman filters that are working together to form, in essence, a third Kalman filter. Okay. Now, there are other things that are going on. There's signal conditioning, because you just want to get rid of the electronic noise that's independent of the noise of the measurements. Analog to digital conversion, because some of these things you're measuring a voltage and you have to convert that into a digital signal so you can use it in calculations. So you see here some of the different inputs, the GPS, the modem, power. The GPS is Furuno GH80 with an integrated antenna, 1 Hertz update. That's kind of typical. A digital modem. And a modem is basically a device that takes an analog system. Well, actually, it takes a digital system, a digital signal, and converts it into an analog signal that can be broadcast like with a radio, because a radio just can't broadcast bits. It has to broadcast something that can be carried by an electromagnetic wave, so basically it has to be an analog signal that gets transmitted. And then when it's received, it's reconverted into a digital signal. So that's a modem. We'll talk more about that later. And then there's the bypass circuit, okay? And so we're going to talk about that in the next slide. All right, so you're sitting there on the ground, you're watching this thing, something happens. Maybe your program just fly through waypoints and all of a sudden an airplane's coming along and you have to take manual control to take evasive action, whatever, okay? So what the bypass circuit, so the whole time the bypass circuit is sitting there, and if it's on autopilot, then the bypass circuit is taking the inputs from the autopilot and passing those along to the control surfaces. So the autopilot is saying, you know, move the aileron this way. Bypass circuit says, okay, yeah, I'm supposed to be listening to the autopilot, so yeah, I'll do that, and I'll send that along, and the ailerons will move the way they're supposed to. Now, what can happen is, and we'll talk about it in the next slide, how this has happened. But basically, you can send a signal to the bypass circuit that says, hey, I need to take manual control. I need to control this thing from the ground, not the autopilot, but from joysticks. All right. So you send it this signal. It says, aha, okay, I'm going to stop taking stuff from the autopilot. I'm going to let the signals that come from the controller on the ground, the manual controller, and send those to the control surfaces of the airplane. Okay. Now, so these joysticks, they're basically electrical servos. So when you move them, there's a voltage change, and that voltage change becomes a digital signal that gets transmitted up. And so the stick positions, the little joysticks on the controller, those positions become the control inputs to the airplane, and also they can be logged later because you want to find out, okay, did he do it right? Say there was a crash. So were the controls, were the commands sent the way they should have been? Was the guy giving proper control inputs? Maybe he was, and something happened to the airplane, and so it's not his fault. But maybe the pilot didn't do something he was supposed to, and that led to the crash. Okay, so you can actually record that information. Okay, so this is what's going on. Okay. So there's some channels on this thing. Channels 1 through 4 and 6 through 8 are decoded into values representing the servo pulse high time. So that has to do with the control inputs. Channel 5 is decoded separately and used as a control signal. Okay. If the channel 5 pulse falls below a set threshold, the microcontroller switches the digital multiplexer to connect the RC receiver servo outputs directly to the servos, a mode known as pilot and control, as the aircraft is controlled by a human pilot through the 72 megahertz control link. All right, so what happens is the bypass circuit is sitting there looking at channel 5, okay, and it's supposed to be high, and typically these digital signals, high as 5 volts and low as 1 volt or something like that, okay? So it's sitting there looking at it. As long as it's staying high, as long as it's staying 5 volts, it's saying, okay, everything coming from the autopilot goes to the servos, goes to the control surfaces. But if that signal drops, goes low, then it says, nope, I got to give control to the guy on the ground, okay? And basically, there's a button on that manual control unit. You push that button, and that's what sends the signal low and says, okay, now I'm taking manual control, and then you fly it using the joysticks, whatever. Then you can, later on, you can either you push a button on the manual control or you do something in the autopilot. It may vary from one system to the other. I think in the Piccolo, you actually do something in the software, in the laptop, to say, okay, I'm going to take control again. I don't remember for certain right at the moment. And I think it varies from system to system. Okay? But basically what's happening is the bypass circuit is sitting there watching that particular signal. If it drops low, it says, okay, forget you, autopilot. the person on the ground is flying it now. Channel 5 pulse rises above the threshold. The digital multiplexer connects the autopilot servo outputs to the servos, a mode known as computer and control mode, as the autopilot has control of the aircraft. that signal goes back high. It says, oh, okay, everything's fine, and go back to letting the autopilot fly the airplane. Okay. So this bypass circuit is sitting there deciding who gets to control the airplane. And the way it decides that is by monitoring that particular channel. All right. Well, this is the ground control station. Basically, it's a laptop, and you see the one box of circuitry there, which includes the modem. There's a little antenna. They call those rubber ducks. Don't know where the name came from, but that's kind of typically what they're called. And then you see the manual controller there and a battery for the modem. Okay? So that's the ground control station. So in that box next to the computer is the same type of digital modem that's on the airplane itself. So you've got two of the same type talking to each other. The Aerocom modems have a 5-kilometer range without the use of directional antennas. So this is considered an omnidirectional antenna. Okay, so there's no dish. It's not pointing in a particular direction. It's broadcasting equally in all directions. Okay, so that's what's used for the ground station communications antenna. Okay. Now the third component is the user interface. That's the laptop and the software. We're going to talk a little bit more about the software here in a little bit. Then you've got, so this is controlling the flight of the aircraft. Then if you've got a payload on board, typically it's got its own communications link. You've got a separate laptop and a separate modem talking to just the payload. Okay. Sometimes, and like on the R16, the way we turn the payload on and off is through the Piccolo autopilot. So there's a command in the Piccolo, the aircraft autopilot software system, that allows you to turn on the payload, and then once the payload is on, the payload computer talks to it. Okay, so now let's talk about the software. We talked about the hardware. We'll talk now about the software. The autopilot software is responsible for attitude estimation. Okay, we've already talked some about that. Processing the sensor data, parsing the GPS data, and what that means is you take those, remember the signals from the satellites, where you take all those signals and then figure out where you are, controls the aircraft, and then handles communications with the ground control station. So that's all what all the software does. It's written in this particular language, Dynamic C. We've already talked about the core module that's used. And the software's purpose is to provide an easy-to-use graphical interface to the autopilot. The ground station runs on a Windows-based laptop computer. All right. So this is a schematic of the software. Okay. So on the left, you've got the main loop. Okay. So that's running kind of all the time. It executes the core algorithms for low-level control and sensor processing. So notice this main loop here for a minute in the diagram. First step, sample sensors. So you get the input from the pressure, the gyros, accelerometers. That's happening very frequently. You process what you're getting out of those. That's the integration and everything. Then you're going to estimate the attitude. Well, at this point, you take in some information from GPS. All right. So now you know which way the airplane is heading, so forth. Now, you get in the low-level commands, which says, I want a particular altitude, I want a particular airspeed, particular heading. Okay, so that's that maintaining flight between waypoints. And so that goes into low-level PID control loops. Those control loops then figure out what commands need to be sent to the servos. Okay, and so that goes to the servos, actually goes to the bypass, and then the servos themselves. Okay. So that's the main loop, and it's running at 130 times per second. So it's executing all this stuff 130 times per second. And I've just gone through the other steps. Now, if you look at the other side, you have what are the concurrent functions. So these aren't necessarily running all the time. Some of them are event-driven. So parse digital comm data. You send up a different command. Well, that's not happening all the time. It's only happening every so often. So, okay. It's sending standard telemetry back to the ground. That happens every so often. It just, whatever it's figured out, it sends it to the ground. Or maybe it just reports. This may be could either be the on board or on the ground. Okay. When you get to GPS stuff, not only does it go into control of the airplane, but just goes into telemetry. Telemetry is all the information about what the airplane is doing that gets sent back down to the ground. Well, obviously, if you've got a GPS location for the airplane, you want to know where it is. So typically there's a moving map display, and the GPS information basically tells you where the airplane is. So you want to know that. Then you have the high-level control. Again, that's where you're saying, okay, I want to go to the next waypoint. I want to go through these waypoints. So that goes into the mid-level control navigation. So that's kind of, all right, I'm here and I want to go to the next one. There's the occasional time when the bypass is activated and you have to basically give manual control over, but that's not happening all the time. It doesn't happen every time the loop executes, just ever so often. And then there's a data logger, which just basically records all the stuff and saves it for future analysis. So you've got the main loop, which is running continuously, doing all the stuff to make sure the airplane's doing what it's supposed to be doing. Then you've got the concurrent functions, which are being executed as needed. Okay. So I've just gone through this. I always do this. I always jump ahead. But the concurrent functions, they parse data from the digital modem. So whatever stuff is coming in from the digital modem, it figures out what it is, sends a standard telemetry package back to the ground station, gets the data from the GPS and figures out where it is. Then it takes some of that, sends it back to the ground. Mid-level navigation functions, high-level fail-safe functions, filing the loop data, run the data logger. So actually, I talked about that in the previous slide. Okay, so that's what's going on in the software. We talked about the hardware, and this is what's going on in the software. Okay, so now let's talk about waypoint navigation. So this is actually how you program the flight, how you tell it to go. I want it to do A and then B and then C. Okay. So what they've done is they've created a library of commands. There are 8 different waypoint commands that they have done. And so the waypoint navigation script uses the low-level control algorithms to navigate the airplane, either by commanding heading, altitude, and velocity, or commanding roll angle, altitude, and velocity. If you command heading, altitude, and velocity, that takes you from one waypoint to another. It tells you which way you want to go and how high you want to be. When you get to a particular waypoint, you may want to orbit it. You may not want to just move on to the next one. You may want to orbit it. So then you command a particular roll angle, because if you roll it, it's going to bank at a certain angle. That's going to put it basically on a circular flight path until you change it. So that would be to orbit a point. And then which one it does is determined automatically by the waypoint command that's being executed. The waypoints are executed sequentially in the order they are uploaded by the user. So you basically just stack them in. You put them in one by one, and it goes through them in that order. All right. So we're going to talk about the 6 types, and then there are 2 other things that they talk about. So first of all is go to XY. That's the command, go to XY. This is a relative position. So the GPS home position, that's the origin. That's 0, 0. And then if you say go to XY, that means go to a position that's X meters east and X meters north of the GPS home position. So we launch, and there's a, say the trailer or whatever, that's 0, 0. I want it to go 100 meters east and 200 meters north, and so that's what it does. That's the XY. The autopilot then figures out, all right, well, I know where I am, I know where I want to be, so I need a heading. So the autopilot figures out what the heading has to be and sends that to the airplane. And so it uses the heading, airspeed, and altitude control. You specify a particular waypoint radius because you're not going to hit it exactly, or you may hit it close, but basically as soon as so it's measuring its position as it's approaching the waypoint. As soon as it gets close enough, as close as you specified, it says, okay, I'm done with that command. I move on to the next one. Okay. And so, so for example, maybe you're going 100 meters east and 200 meters north. Well, you get to within, say, 10 meters of that, or 5 meters of that. and say, all right, I'm close enough. I've finished that command. I move on to the next one. So there are basically parameters or arguments for these commands. The meters east, the meters north, the altitude, and the airspeed. Okay. Then there's a parameter you set elsewhere, which is the waypoint radius, and that'll be the same for all different waypoints, unless you change it somewhere in between. Okay. All right, so that's the first. So all of the, all you have to do is say go to X, Y with all these different arguments, and then all the software figures out, takes that information, figures out what the airplane, what commands it needs to send to the airplane to do that. Right. Now, the next one is go to legal. All right. This is where you specify an absolute position. You specify degrees, longitude, and latitude. Okay. This is the only one where you specify location in terms of longitude and latitude. Everything else is relative, but this one is absolute, and so it's go to legal. Okay. Again, it knows where it is, knows its longitude, and latitude, knows where it wants to go, figures out a heading, uses the altitude, speed, and heading hold command to get there. When it gets to within the given radius of that waypoint, it says, okay, I'm done, I'll move on to the next one. And these are the arguments for the command. Degrees, longitude, degrees, latitude, altitude, and airspeed. Okay? So two different ways to go from point A to point B. Now, once you get there, then maybe you want to loiter. Maybe you want to orbit that point. Okay? And notice this is a relative. They don't have a loiter legal. Okay? They just have loiter X, Y, so you only can use the relative thing. All right, so once you've got to a particular point, this command figures out, okay, I want to, you specify the radius of the orbit. Okay, I want to orbit this point with a 100-meter radius or 50-meter radius or whatever. Well, the controller figures out, okay, to make that circle at a particular speed, I need a particular bank angle. So it figures out the roll angle, all right? and then uses the roll, altitude, and speed hold. And you tell it how long, and once it's orbited that point for that length of time, it quits. Okay, and then it goes on to the next one. Now, if you put in 0 for the orbit time, then when it gets there, it'll just orbit indefinitely until you go in manually and tell it to do something else. So these are the parameters that it requires: meters east, meters north, altitude, airspeed, orbit time, and orbit radius. Okay. So once it times out, it goes to the next point. If you put in 0 orbit time, it'll just stay there, and it'll do it at the radius that you want. Okay. Then land XY. All right. This would vary from aircraft to aircraft, because some aircraft, they can land anywhere if there's light, and they have really low landing speed. You just plump them onto the ground, they're all right. Others, you gotta have a runway. All right. So this is the landing sequence. So land XY executes a landing sequence around the position specified in meters east and meters north of the GPS home position. Again, it's a relative measurement. So this is what happens. The landing sequence first orbits the aircraft around the landing position while holding airspeed. All right, so it brings it to where it wants, and then it orbits that position, okay, with some radius. Then the autopilot cuts the throttle, and the aircraft starts coming down and descends, so it's still in this orbit. Now it's spiraling down, and it's regulating the airspeed using the pitch from the airspeed PID loop. So just, it's coming down, but it's keep maintaining airspeed. When it finally gets down to a particular altitude specified by the flare height, and I think I have that misspelled, maybe not. I think it's supposed to be FLARE. But when it gets to a certain altitude, and there's a parameter setting, the flare height, the autopilot will, so remember, so if it's spiraling, it's banked. So the autopilot attempts to level the aircraft by commanding a 0 roll angle to the aileron from the roll PID loop. So it's spiraled down, it's finally at the flare height. Wings go level, so now it's flying in a straight line again. If the flare height is set to 0, the autopilot will not attempt to flare the aircraft. And then when it gets down there, basically then it flares and lands. I think that it glides in, think that it cuts the motor all the way to 0 in that first step. When it cuts the throttle, I think it cuts it all the way to 0. So it glides down. When it gets to the height, it's wings level, starts flying a straight line, flares, nose comes up, it stalls, and it plops onto the ground. It's light, made out of styrofoam, you know, it's okay. All right, so these are the commands, the parameters: meters east, meters north, the altitude. Yeah, so this is the altitude it's going to start at. It's going to start to spiral down. The airspeed that's going to hold is coming down. The orbit radius, and then the flare height. Okay, so it spirals down, gets down low, wings roll level, starts flying a straight line, flares, comes to the ground. Okay, takeoff. Now this is automatic takeoff, and this is one of those. Pretty sure this is one of those airplanes where they just throw it in the air. Okay, so the takeoff, and so there's no XY, it's wherever it is, it executes the takeoff sequence at, you know, the current GPS position, wherever it is. All right, so first of all, it commands the aircraft to hold a constant pitch specified in the parameter takeoff pitch, okay, while using aileron from roll PID loop to hold a 0-degree roll angle. So the wings are kept level. The autopilot commands full throttle, and the airplane attempts to hold a particular pitch angle. And if it's, you know, positive pitch angle, it's going to climb. Okay. Once the aircraft reaches the airspeed specified in the rotate airspeed input field, autopilot enables the altitude tracker and commands an orbit at the current GPS location with the orbit radius specified in the orbit radius input field. Okay. So if it gets going fast enough, basically the autopilot says, okay, it's taken off. It's flying at the speed it needs to be flying. So now it's going to figure out, okay, so I'm going to turn on altitude tracking, and then it's just going to orbit the launch point. Okay. If the aircraft does not achieve the rotate velocity within the period of time specified in the parameter takeoff, rotate, time out, the takeoff sequence is aborted, and the autopilot commands 0 throttle in an attempt to land the aircraft. If something goes wrong, if it doesn't, there's a certain length of time that's supposed to reach the flight speed. Okay, if you imagine if you're tossing this thing in the air, it's going to be fairly short. And if you throw it and the engine doesn't throttle up for some reason and it decides, hey, I'm not flying fast enough. And you know, I've been in the air a couple of seconds, I'm not flying fast enough. I'm going to go ahead and kill the engine and land, and then they figure out what's going on. Okay, so that's what happens. All right. Now, so in the previous step, when it starts orbiting, it's climbing. Okay, so it's still climbing, and once it finally reaches the altitude that's specified in the command, the takeoff command is done. You basically finish that waypoint command. You're ready to move on to the next one. Okay. So takeoff command takes the following parameters: the command completion altitude, what's the altitude that's considered to be flying, and you know can start its mission. The rotate airspeed, which is the airspeed it has to hit in a certain length of time, or else it throttle off and it comes down. And the climb out orbit radius. So it's going to be thrown in the air. It has a certain length of time to reach a certain speed. If it reaches that speed, it's just going to go into an orbit around a point and climb till it gets to the specified altitude. And then that will be considered a successful takeoff, and it moves on to the next point. Okay. If any of those things don't happen, then throttle off, glide down, let the crew find out what went wrong. Okay. Repeat. If you're going to fly sequences of waypoints, so you just have to give it a waypoint number, and it will just keep doing that particular waypoint command. Repeat causes the waypoint navigation script to execute the waypoint command specified in the waypoint number input field. Command is used to repeatedly fly sequences of waypoints. So you're basically doing a box. So you're doing a rectangle, and you want to do that over and over. Well, you've already told it how to get around the box once. So when it comes to the end of the first loop, you just say repeat waypoint 2, repeat waypoint 3, repeat waypoint 4. Okay. And so then it'll just keep flying around that box. Just keep doing the same waypoints over and over. And you don't have to program them all in over and over. You just use the repeat command. As I pointed out earlier, there's only one legal command, which is actually a little odd because a lot of the autopilots now are basically you have a moving map display. Okay, like a tablet will have a map on it. You just point to the tablet, put your finger on the points you want to fly through, and at each point you set the altitude and you're done. Okay, so like the DJI Phantom and some of the others like that, that's basically the way it's controlled. And so those are absolute waypoints because you're not relative to anything. It's reading. It has that map from Google Earth or whatever, and so each point you touch, it knows the latitude and longitude of each of those points, and so it creates the waypoints that way. In this particular version, and this is an older version, they may have upgraded it since to have latitude and longitude inputs. But in this case, they only had one, and all the rest were relative. Okay, you had to know, kind of had to, basically you get out the Google Earth map, you figure out the points, or you figure out their coordinates relative to, the home GPS location or whatever. Okay, now there are two other high-level control algorithms used by the autopilot. So these are kind of in the background at the top level, and these are the things that take over when stuff goes wrong. So the first is a lost communication go home fail safe, or just called the go home fail safe. And this is the lost link thing. If communication is lost between the aircraft and the ground control station, then this high level loop kicks in and basically figures out, okay, I know where I am, I know where the ground control station was, we'll go home. Okay. The second is the pilot and command lost communication fail-safe, or PIC fail-safe. Purpose of this is to utilize the low-level control and navigation capabilities of the aircraft to safely fly the aircraft in the event of a lost communication scenario when the autopilot is in piloted command mode. So you've got manual control, okay, you're flying the airplane with the joysticks, and all of a sudden you lose that communications link. All of a sudden now you're moving the joysticks and nothing is happening on the airplane. So that's a lost communication during manual control. So there's another high-level loop that takes over and sends it home in that mode when it happens in that mode. Okay. So, and this is similar to the way the RS-16 works. The autopilot will send a navigation status packet to the ground station every time the autopilot receives a packet from the GPS receiver. All right, so the autopilot gets the input from the GPS, sends a status packet down. The ground control station says, all right, I got the packet, and I'm letting you know I got the packet. So it sends an acknowledgement packet back up, okay? And then, now for this to work, the autopilot has GPS lock. So you've still got good communication with the GPS satellites. So you're still getting information about the airplane location from GPS. Okay? So under these premises, there will be two-way communication between the autopilot and ground station at least once per second, because every time it gets an update from the GPS, it sends a packet down. The ground control station says, I got it, and it lets the airplane know it got the packet. Okay. Now, the airplane, every time it sends one of those packets down, it checks to see if it got an acknowledgement packet. And sometimes it doesn't. Sometimes there's just little glitches in the communications. It doesn't necessarily get every acknowledgement packet, but it gets most of them. Okay. But so what it does is it counts. If there are acknowledgement packets that are missing, it counts those. It says, all right, I sent one down, got one back. I sent one down, sent a second one down, got one back. So there's two. Okay. Sent one down, sent one down, sent one down, got one back. Okay, so then there's three. All right. Well, it counts those times it sent it down before it got one back. And if it sends a whole bunch of them down and never gets something back, there's a threshold. All right, I've sent it 20 and I haven't gotten anything back. I know there's a problem. Okay, so it assumes that the communication link is down, and whoop, okay, I've lost. I'm not talking to the ground anymore, so I'm going home. Okay, Once the GPS home position is reached, the autopilot is configured to orbit at a constant radius about the GPS home position. So it gets there, all right, I'm here, and it just circles around, and then people on the ground have time to see if they can figure out what's going on and reestablish communication. And if they can't, then it just eventually the battery runs out, and it spirals down and lands. Okay. Flying the aircraft to the home position is intended to reduce the line of sight distance of the aircraft and allow for communication with the aircraft to be reestablished. Usually the reason why you lose communication is that you're at the kind of the maximum of the radio range. That's typically what happens with the RS-16. And so the idea is, well, you bring it back close, and then maybe you reestablish communication. And that is what's happened every time we've had a lost link with the airplane. We get it back close enough, we reestablish link. Okay? So that's what's happening here. And it's the same kind of thing. There's an acknowledgement ratio. And so there's an acknowledgement ratio on the ground control station also, because it's sending packets up to the airplane and then checking to see if it gets an acknowledgement. And so there's a ratio. Maybe it's getting 95% acknowledgement. It's missing a few, but yeah, that's okay. But if it drops below some value, then there's a possible issue. And if it drops below another value, then it's considered lost. And if, of course, it's not getting it at all, then that's how you know on the ground that you've lost link. So that's happening on both ends. Okay, so this is what that window looks like, the graphical interface looks like. So you see kind of the heads-up display on the left, shows the attitude, pitch and roll. Then there's a moving map display on the right that shows the waypoints and shows where the airplane is. In the middle is, shows the waypoints. And so notice it's there's waypoint and loiter, then maybe there's low battery indicator. So these are some indications, but also it's talking about the going through the waypoints. So notice the landing at the bottom. I think at the very bottom in the middle is where you actually enter the waypoints. And then on the left is basically the telemetry. This is telling you what the airplane is actually doing. Notice roll, in this particular case, the desired was 46.35 degrees, the actual is 40.7 degrees, so some error there, but showing what's commanded and what's actually measuring. Okay. So this is what the pilot is looking at, and it has these different tabs, and you can do different things. So you can upload the waypoints, you can monitor the waypoints, and so that's what it looks like. Unfortunately, I don't have a good video. Now, I've actually this video that's in the link here, I actually put it up in lecture 2. So if you watched it then, you've already seen it. It shows a group, Missouri University of Science and Technology, who use this autopilot, and they did some tuning. Okay, that basically you can, by tuning some of the parameters, you can improve, and that's what the video shows. So I'll let you watch the video, and you can see how one of these things work. And then you can basically look around YouTube and find some other examples. That concludes this lecture, and the next unit we'll talk about the command and control equipment, the ground support equipment, radios, launchers, that kind of stuff. So all that kind of gets lumped into the ground equipment unit. So that concludes this lecture.